Okay, so welcome back to the last video for section 5.1, our approximating area by rectangles. So we're going to start off with this example. X to the fourth. And I want to look on the interval 0, 1 with 4 rectangles. So remember, the idea is you have some graph, and I have it on 0, 1, and I can look at what's the area bounded between those two x values. Okay, so if we're going to approximate by rectangles, we need the rectangle width and length. The width, or I've been calling it delta x, is the difference of the interval divided by the number of rectangles, or in this case, 1/4. Okay, so then we could break up these into, say, 0, 1/4, 1/4, 1/2. You're just adding 1/4 each time, coming from here. 1/2, 3/4, and 3/4 1. So up to this point, we've talked about, well, how do you do L4 and how do you do R4? So why don't you pause the video right now and do those calculations. I hope you did those calculations. Remember, the width is 1/4, and then the length is f of whatever your endpoint you're using. So in this case, L4 for left, we want to use the left endpoints. And we add them all up, and what do we get? Well, you can plug them back into the function, and as a fraction, you'll get 97 over 1024, which is approximately 0.09473. What about R4, using the right endpoints? Well, it's the same, you're just picking different x values. You start at 1/4, you're using the ones on the right. And you'll get approximately 0.345703. Okay, so that's the left and right endpoints. I will say neither of these are particularly close to the true area. That is going to be 0.2. So you might think, well, is there other methods we could do that might be closer, still using only 4 rectangles? And so I'd like to, with that, introduce some other types of approximations with these rectangles. One of them is called a midpoint sum or midpoint rule. As the name suggests, so we still have the same width, but for our length, doing the midpoint, or M4, for midpoint rule. still have the 1/4, but then for my f value, I need to have something in this interval. But instead of using the edges of the interval, the endpoints, why don't I use something right in the center of the interval? Particularly, I could use the midpoint. And how do we get the midpoint? Well, if you remember, midpoint between 2 points is you add them up and you divide by 2. In the first case, you would get 1/8. And for the second one, it would be 1/4 plus 1/2 divided by 2, or 3/8. And you continue down the line. And this gives you a different approximation than we've been doing. It just requires this extra step of finding the midpoint of each of the intervals. And what do we get? Well, we're going to get, this is going to be 1/16384 plus 81/16384 plus 625/16384 plus 2401/16384. Once you plug in each of these into the original function and multiply it by 1/4, those are the fractions you get. And when you add them and reduce the fraction, you'll get 777/4096, which is approximately 0.1897. Now, if you look at what we had for L4, that was approximately 0.095, and R4 was approximately 0.346. So if you look at it, notice the midpoint is a lot closer to our true area of 0.2 than L4 and R4. So the midpoint in this case did a better job of approximating. The only thing was it required that additional little step that we had. Okay, so what about other approximation techniques? Like, what other ways can we approximate our area? Well, there's one that we're going to talk about now. You have what's called a lower sum and an upper sum. The idea with a lower sum and an upper sum, if I take, so let's start with one of these little intervals. So let's just pretend this x value is one of the intervals. On the y, that will correspond to this part. So if we draw it down here, we have this thing. And we want to find that area. So the idea behind a lower and upper sum is those ones they want you to give you a guaranteed underestimate, one that's definitely going to be less than the true area, and a guaranteed overestimate. Now, how do we do that? Well, with what we're going to call the lower sum, the underestimate, we want to choose so we still have our width, but for our length, our f of insert number here, we want to choose the y value so that all this area is all going to lie underneath this curve. Notice if I choose this endpoint, it all lies underneath. But if I choose this one, well, now I have this rectangle, and you have this little extra bit that doesn't lie underneath. And same if you choose point up here, you'll have that other bit that doesn't lie underneath. So you could say, well, what distinguishes this bottom one from the other ones? Well, notice the y value. This y value is an absolute min for the function on this interval. So lower sum, or sometimes called inscribed sum, we want to use the absolute minimum value. That way we're guaranteed an underestimate. Now, upper sum, you want to do the reverse. Use an absolute max value. So whenever we have this question of finding upper or lower sum, because we're talking about absolute max and min, what does that mean? Well, that means we're going to have to use our techniques from last chapter to find on each one of these intervals what is the absolute max and min. So we could do that. First derivative test. You take the first derivative, set it equal to 0, and solve. Our critical number is only at 0. You can make your little chart, plugging in your test points to the first derivative. What do you get? Well, you get decreasing on less than 0 and increasing on greater than 0. So to find your absolute max and absolute min on, say, the first one, 0, 1/4, you need to say, well, what is f of the endpoints and what is f of the critical points? However, notice that the only critical point is 0. So in this case, we're not going to need to test that critical point. Now, f of 0 is 0. F of 1/4, well, that's 1/4 to the 4th, which you can do in your calculator, is 1/256. So, in this case, 0 is our absolute min, and f of 0 is our absolute min, f of 1/4 is our absolute max, which makes sense because on that interval you're increasing. So, when doing what we'll call the inscribed or lower sum, it'd still be the 1/4, but now it's f of, on this interval we want to choose the absolute min, so we'll use f of 0. And you could do that for the other ones. What you'll get is 1/4 f of 1/4 plus 1/4 f of 1/2 plus 1/4 f of 3/4, which is the same thing as the left sum. So the reason we're doing this way, remember, is not because we're trying to get a closer approximation, but because we're trying to guarantee an under approximation, get a bounds in some way. Which is why this This one, the guarantee and under approximation, just compute the left endpoint sum. It will not always be a left or right endpoint sum. For example, if we change this to -1, 1, that will change our width to 1/2, which will in turn change each one of these intervals. Our work for finding critical points stays the same because we have the same function. But now, you have to say on each one of these intervals, where is the absolute max and min? For example, on this interval, it's not going to change. You're still going to have 0, that left endpoint. And same here. You're still going to have 1/2. But you could check, and because on negative numbers, the interval is decreasing, on this one, it won't be the left endpoint, but it will be the right endpoint, because f of -1 is 1. But f of -1/2 is going to be 1/2⁴, or 1/16. So, in this case, it'll be f of -1/2. And similarly, this one will be f of 0. Now that is not the left sum, but it's also not the right sum. So in general, the inscribed or lower sum can look a little different than any of the ones that we've looked at. But a lot of times, if the functions are nice enough, it will correspond to a left or right sum. But not always. Now on your worksheet for today, there will be one inscribed that you'll have to do so that you get practice. With these worksheets, I'm looking that you put forth an attempt. As you probably noticed, they're not graded in the traditional sense of me saying, is your answer right or wrong? But they're more, I want you to try these problems and get practice. Okay, so the last little bit of this section, what I'd like to finish out with is a more application-based. Why are we looking at areas? I sort of just pulled it out of there, where I was like, okay, let's look at areas under a curve. But why was that important? Well, to see the importance, let's go back to looking at what the area of a rectangle is. Well, area is length times width, right? And in the problem, we know what the width is and we know what the length is, and we're trying to find area. It's sort of similar to whenever we were talking about derivatives, you had the whole velocity problem where you had two things you often knew, distance and time, and you were dividing them to get your new unit. That is what the derivative helped with. This idea of area, instead of helping with things that you're dividing, it's helping with things that you're multiplying. So in general, this idea of finding area will help any time we have two units we're multiplying to get a new unit, and we want to find out information about it. For example, if you might recall, d equals rt is our formula for the distance. If you know a speed and you know time, then we can find distance. Now let's suppose we have this situation. The speed of a runner increases steadily during the first 3 seconds of the race. Find estimates for distance. When it's talking about estimates, just to give you context, that's saying find lower and upper sums. Now we know D equals RT, and now this is going to give us at what time, at time 0, say you're starting at 0, but at 0.5, this is now your new speed, 6.2, and it's giving this table. So I'm going to just quickly write this down. Okay, so it's giving you this table, and it's saying, we know D equals RT, so because it's multiplication in that sense, we could use the idea of area that we've been using for approximating to find estimates for the distance. So if we want to do a lower approximation, that is an under approximation, we need our width and our length of each one of these. We can think about there being a rectangle from this one to this one, so that little bit. So the width would be 0.5, right? You're just subtracting the 2, the times. And then what about our length? Well, if we want a lower one, we want to choose the smaller of these two. In this case, 0. And then we go down the line. Our next two are 0.5 and 1. So we look at the lower, that's 6.2. And then 0.5. Between these two, we would look at 10.8. And you continue this all the way to the last one. And it gives you 19.4. Now let's write out what all those terms are, just to be clear. And this lower sum, you could put this all in your calculator, you'll get 34.7. And the units would be feet, in this case. I didn't really give you the units, but the problem from the textbook itself will give you those units. Okay, so that's a lower sum. I'll put it up there. What about an upper sum? This problem doesn't change too much with an upper sum. You still have the same widths. But now, between the two numbers, you have to look at the bigger number. So on the first one, between these two, you have to look at what number is bigger if you're doing an upper sum. And so I'll write down all the ones, but basically you're looking at each of these pairs and saying which of the two numbers is bigger. And what does that give you? Well, this upper sum is going to be 44.8 feet. And that's our estimates for the distance. Is what we're going to have in the end is that our true distance, I'll call it capital D, lies in between these two numbers, is somewhere in between 44.8 feet and 34.7 feet. Okay, so that's all for section 5.1. So if you have any questions, send me a message in Canvas, comment onto this video. Sure to ask lots of questions. I know this section is a little bit more, might feel at times a little bit more conceptual than the other material, and it's not going away. So just be sure to ask lots of questions, and next video will be continuing on to the next section, 5.2. which will be a lot of related material. So I will see you all then.